Hello and welcome to our channel. Ever wondered why gold is found in certain mountains, or why some ocean floors are rich in valuable metals? The answer lies deep beneath our feet, in the slow, powerful dance of Earth's tectonic plates. Today, we're re-diving into the fascinating world of plate tectonics and uncovering how their movement is directly responsible for creating the mineral deposits we rely on every single day. From the copper in our electronics to the gold in our jewelry, it all starts with geology. So, what exactly is plate tectonics? Imagine Earth's outer shell, the lithosphere, isn't one solid piece. Instead, it's broken up into massive, rigid plates, kind of like a cracked eggshell. These plates are constantly moving, floating on the semi-fluid layer beneath them called the asthenosphere. Now, this movement is incredibly slow, about the same speed your fingernails grow. But over millions of years, it's powerful enough to build mountains, create oceans, trigger earthquakes, and fuel volcanoes. And, as we'll explore today, it's the engine that drives the formation of mineral resources all over the globe. But where did this groundbreaking idea come from? It wasn't just one person's discovery, but a brilliant puzzle pieced together over decades. The story really begins in 1912 with a German meteorologist named Alfred Wegener. He proposed the radical idea of continental drift, suggesting that continents weren't fixed in place but had actually moved over time. He pointed to evidence like how the coastlines of South America and Africa seemed to fit together like puzzle pieces, and how identical fossils were found on continents now separated by vast oceans. At the time, his theory was largely dismissed because he couldn't explain what force was powerful enough to move entire continents. The mystery started to unravel in the 1960s. Scientists like Harry Hess and Robert Dietz were mapping the ocean floor and made a stunning discovery. They found underwater mountain ranges called mid-ocean ridges, where new oceanic crust was being formed and pushing the older crust away. They called this seafloor spreading. This was the missing piece of the puzzle. It provided the mechanism for Wegener's continental drift. Finally, geologists connected the dots between continental drift, seafloor spreading, and the patterns of global earthquakes and volcanic activity. All these ideas came together to form the comprehensive theory we now call plate tectonics. It completely revolutionized our understanding of the planet. To understand how this movement creates minerals, we first need to look at how these plates interact. There are three main types of plate boundaries, and each one creates a unique geological environment for mineral formation. First up, we have divergent boundaries. This is where two plates are moving away from each other. As they pull apart, hot magma from the mantle rises up to fill the gap, creating new crust. The most famous examples are the Mid-Atlantic Ridge and the East African Rift Valley. At these locations, hot, mineral-rich water, known as hydrothermal fluids, circulates through the newly formed volcanic rock. These fluids dissolve metals like copper, zinc, and lead from the surrounding rock. When this superheated water meets the cold ocean water, the dissolved metals rapidly precipitate out, forming incredible chimney-like structures called black smokers that spew out a dark cloud of metal sulfide particles. Over time, these particles build up on the seafloor, creating massive sulfide deposits, which are a major source of many important metals. Next, we have convergent boundaries, where two plates collide. What happens next depends on the types of plates involved. When a dense oceanic plate collides with a lighter continental plate, the oceanic plate is forced to bend and slide beneath the continental plate in a process called subduction. This is a hugely important process for mineral formation. As the subducting plate sinks deeper into the mantle, the increasing heat and pressure cause it to release water and other volatiles. This water rises into the overlying mantle, lowering its melting point and generating large amounts of magma. This magma is less dense than the surrounding rock, so it rises towards the surface, forming a chain of volcanoes on the continent known as a volcanic arc. The Andes Mountains are a classic example. This magma is incredibly rich in dissolved metals. As it moves and cools, it can form massive ore deposits of copper, gold, molybdenum, silver, and tin. These deposits, known as porphyry deposits, are some of the largest and most economically important mineral sources on the planet. Sometimes, two continental plates collide. Since both plates are relatively light, neither one wants to subduct. Instead, they crumple and fold, pushing up enormous mountain ranges, like the Himalayas, which formed from the collision of the Indian and Eurasian plates. The intense pressure and heat during this collision can metamorphose existing rocks, sometimes concentrating minerals like jade, graphite, and industrial minerals like garnet. The third type of boundary is a transform boundary. Here, two plates slide horizontally past one another. The San Andreas Fault in California is the most famous example. While this motion doesn't create or destroy crust, the immense friction and stress create extensive fault zones with numerous cracks and fractures in the rock. These fractures act as pathways for hydrothermal fluids to travel through. As these fluids move, they can cool and deposit minerals they've picked up from deeper rocks, filling the cracks to form mineral veins. These veins can be rich in gold, silver, and quartz. So even this sideways sliding motion plays a crucial role in concentrating valuable resources. So let's tie it all together. How exactly does this grand-scale plate motion create minerals? First, the heat and pressure generated at plate boundaries, especially at subduction zones, are perfect for melting rock and creating magma. This magma is the primary source material for many mineral deposits. Second, as this magma rises, it carries dissolved metals with it. It can either cool slowly deep underground, allowing minerals to crystallize and concentrate, or it can feed volcanic systems on the surface. Third, we have the action of hydrothermal fluids. Plate tectonics creates the fractures and heat sources necessary for water to circulate deep within the crust, dissolving metals and then redepositing them in concentrated veins or on the seafloor. From the massive sulfide deposits at mid-ocean ridges to the giant copper and gold systems in volcanic arcs, the connection is clear. Mineral deposits are not just randomly scattered across the Earth. Their locations are fundamentally controlled by the dynamic, ongoing process of plate tectonics. Understanding this link is not just academic. It's a vital tool for exploration geologists. By studying the tectonic history of a region, they can predict where to find specific types of mineral deposits. A geologist looking for copper would focus on ancient subduction zones, while someone searching for zinc might explore areas that were once mid-ocean ridges. It's like having a treasure map written in the language of geology. This dynamic system not only shapes the mountains we climb and the oceans we sail, but it also provides the essential raw materials that build our modern world. So, the next time you use your phone or see a skyscraper, remember the incredible journey of its components. They were forged in the fiery depths of the Earth, brought to the surface by the slow but relentless movement of tectonic plates, and concentrated over millions of years into the deposits we can find today. It's a powerful reminder of how interconnected our lives are with the deep geological processes of our planet. Thanks so much for joining us on this geological journey today. If you enjoyed this video and want to learn more about the amazing forces that shape our world, be sure to hit that like button, share this video with a friend, and subscribe to the channel for more deep dives into Earth science. Let us know in the comments what geology topic you'd like us to explore next. See you in the next video.